Welcome to the Embedded System Programming, and this is video presentation for third assignment, that is SPI device programming and pulse measurement. The objective of this assignment is to learn the basic programming techniques in Linux SPI in GPIO kernel modules, and to learn the software structures of SPI driver, and also to develop an application of distance controlled animation. So let us first study difference between SPI and I2C. I2C is half duplex while SPI is full duplex. That is, in SPI we can read and write at the same time, but in I2C we can only perform read or write at one particular time. In I2C, as the data is transferred bit by bit, as compared to the data transferred byte by byte in SPI, the speed of SPI is much greater than I2C, but we require additional number of wires in SPI for chip select. So to transfer data, we need to enable chip select pin. But for sending or writing data into I2C device, we need to send 7-bit address again and again, followed by the read or write bit. So the first task of the assignment is to develop a user application to enable distance control animation using 8x8 LED matrix and an ultrasonic sensor. Let us study the working of ultrasonic sensor. The timer is started as soon as the trigger is sent, and the timer is stopped when the echo is received. So the distance is calculated from the time difference between the rising and the falling edge. So in order to calculate distance of the object from the sensor, we need to keep polling for the rising and falling edge. As the time difference between the trigger and the rising edge is very less, care must be taken that there are no unuseful statements like printf between sending a trigger and detecting a rising edge. Uh, as soon as the rising edge is detected, we start the timer, and we keep polling for the falling edge, and when the falling edge is detected, we stop the timer. So we can calculate the distance from the time difference we get. In order to write the first task, we need to follow these steps. We need to first configure the GPIOs which we are using to connect the trigger and echo pin of the sensor. We need to export the GPIOs, set the direction and their values. After configuring GPIOs, we need to initialize SPI controller, for which we can use the default IOCTL commands to set the mode, and to set the maximum speed of the transmission, or to set the maximum bit per word, that is we can set either to 8 or 16. And after initializing SPI, we need to initialize LED matrix by setting the scan limit, intensity of the LED, etc. For that, we need to read the datasheet properly in order to know the register address and the particular value. After initializing everything, we need to send the trigger and check for the edges at the echo pin. For that, we can use either poll function or select function. Poll function is defined in poll.h, which keeps on checking the value for a particular event. So we can get the distance of the object by using poll function twice, that is one for rising and one for falling edge. Then we need to create a dog pattern which can be controlled by the distance we received from the poll function. As we need to perform two functions, that is displaying dog pattern and getting the distance of the object, we need to make a program multi-threaded so that both functions can be performed at the same time. This is an example of the first task, in which dog either runs or walks in either left or right direction depending upon the distance of the object from the sensor. In the first task, we use the default SPI date driver, but for the second task, we need to develop a device driver with additional functions like IOCTL command to send 10 patterns, which we need to display on the LED matrix, and a write function to send a display sequence of pattern number and the respective delay. And we also need to write a device driver to measure the pulse width using GPIO interrupt and interrupt handler. SPI protocol driver, uh, we need to first refer to the SPI file from Linux cross-reference. So in our driver, we need to add an IOCTL command along with other commands to receive pattern from the user and store it in a global buffer. We also need to modify the write function of the SPI driver to implement logic to separate pattern number and the respective delay. As the pattern buffer is used by both the write function and the display function, we need to use mutex to avoid any race condition. The program should also look for terminating sequence, that is 0, 0. Therefore, whenever we receive 0, 0, LED should turn off and there should be no LED glowing. The display of pattern can take time. We don't want a user program to wait for such time. So we need to implement a program through work queue or kernel thread so that we can save some time. As the pole function used in the first task was not very accurate, we can get the time difference between the rising and falling edge by using interrupt handler. First we need to get the interrupt request number from GPIO underscore interrupt function, and then we can request the IRQ by using that IRQ number. First we need to set the interrupt flag for rising. So when rising has occurred, interrupt handler is called and the timer is started. Then we need to change the interrupt flag to falling by using set IRQ type. And then when the falling has occurred, again interrupt handler is called and the timer is stopped. So we can get the time difference from the timer function. So after writing the drivers, we need to write a user program in which we need to initialize the GPIOs and LED metrics as we did for the first task, and then we need to send the pattern through the IOCTL command which we define in the driver. After sending the pattern, we need to send trigger to the write function of the pulse measurement driver, which will calculate the time difference between the rising and falling edge, which we can get the time difference by the read function and then calculate the distance of the object. So by sending appropriate number of pattern and the time delay, we need to display the animation which is controlled by the distance received from the interrupt handler. Part of the second task, in which the pattern is that the lock unlocks and the LED is glown from left to right or right to left depending upon the distance of the object, and then the lock closes again.